All right, can we start now? 45 for joining. So I welcome all of you once again for basic electronics class once again. And this is a continuation on what we had discussed so far. So we were discussing on transistors, if you remember. And on last day's class, we discussed a very important and a very interesting concept of early effect and how it affects the nature of input-output characteristics of transistors. And in light of that, we had specifically discussed on the CB configuration. If you remember, given the fact that we expect that we can have multiple such combinations of common base, common collector, and common emitter. In that, we started off with common base, and I told you that the input and the output characteristics are the very important family of curves, which gives us an understanding about the operating points of the transistors and how they are to be used. So in that aspect, CB is what we have discussed, and we have found out that with respect to the CB configuration, we can expect a graph which will look very similar to this, the one that I'm showing right now. And I also have shown you the reason for it, the input characteristics, why the graph is going to be like this. And in that aspect, we have discussed the early effect. And as I said also that the output characteristics would look something of this nature, and that is due to the fact that this is where we are getting the output, that is the IC, which is over here. You can observe IC is the output, and the input, the voltage that we are observing over here is VCB. So this is my VCB. So we are varying on the collector to base terminal voltage, and we are getting a response between IC versus VCB. And in that aspect, we have found out that when we are reducing the VCB, that is when we are reaching from 0 to -1 or even further, we can expect that the current will drop gradually. So the collector current is reducing drastically. You can observe the last point, when VCB is negative, the collector base is forward bias, and hence IC will substantially reduce. So naturally, if I want to operate near this saturation region, we won't be expecting a very good response because the collector current will come down. All right, and on the other hand, if I keep my transistor in this active region, how I can keep the transistor operating in an active region? By specifically keeping my input voltage, that is the CB voltage or the collector to base terminal voltage, to be within a certain range. This range actually depends on the transistors being used or the manufacturer. You remember in lab I told you that specifically we are using VC547B, so that's a specific transistor. Now if you change the transistor model, definitely the input output characteristics will give us that what should be the input and the output voltage, or the rating of the input output voltage, to keep the transistor working in the active region. All right, and in that aspect, we have also found out that what is R out, and I told you in the lab also that how we can find out R in and R out. So I'm not repeating it once again over here. Now, in light of that, let me finish off with the configuration itself. So this is one of the factors that I told you, that when this saturation region comes in, okay, when we look at this saturation region, we usually call this for a CB configuration, and if we are reaching a saturation region, then this particular condition is what we call as a switching. Okay, so the transistor will act as a switch if I keep that is in the saturation region. So how it works, I'll tell you separately, but just to understand for the time being, in case of the saturation region, it is used as a switching. Whenever we need a switch, like, so how does the switch work? Like when you are giving a high input, the output will be 0, or when you are giving a 0, whenever you're giving a on, you want to make a switch on, you want to make the circuit, you will switch on, or if you want to break the circuit, you will make it off. The same characteristics will be observed over here in transistor whenever we are using it in the saturation region. How we are doing it, I'll tell you after this. On the other hand, if I consider the other region, which is the active region, if you observe the active region over here, okay, if I keep it in the active region in that way, this ideally is used when we require the amplification. Okay, so whenever, especially with the CE configuration, you will observe that CE is the best suited configuration. I told you that it is the most commonly used configuration of all, and in that as well as you can observe that in the active region, why it is a good amplification, because at that period you will get a very good beta value, and if you get a very good value of beta, the current gain will be very high. So that is why if you give a small input current, the output current will be magnified. So that is why we want to keep it in the active region. Saturation, you imagine in a way that saturation is that the IC or the component is reached its maximum. Like whatever be its efficiency, it has reached to its maximum. So it cannot go further. Whereas in active region means that it is still has a capability of reaching to a maximum value. So that's the difference between an active region or an application in an active zone as well as compared to a saturation region. All right. And as we know the cutoff, I told you the cutoff, I'll explain you right now after this. So cutoff is this part where it is less than 0. You can see this is my 0. So when it is below this portion, the small portion that you're observing, this is where we call as the cutoff region. And when we are looking at cutoff region, that is when both the terminals are reverse biased, okay, then that will be considered as another set of switch. This is called as open switch. That is when it is like when there is input but there is no output, like that. Okay, so when you are cutting, like completely getting it off. So ideally what is happening, you can observe that there are two operations. One is the switch application of transistor, one is switching, and the other one is an amplification. Now in case of amplifier, the active region is what we are working on. So if I just quickly write it down over here. So yeah, so if I write it over here, so there are three methods. One is the saturation. Okay, so when you are reaching at saturation and you're operating a transistor at the saturation level, okay, let me just change this ball point. 1 minute, give me 1 minute. Why it is not going? Yeah, give me just 1 minute. I'll change the color. Yeah, so one is the saturation. And in saturation, what we are looking at, that we are looking at a switching option. What kind of switch we will discuss later. Even cutoff will also have the switching pattern. Okay, so the switching mode is operating. On the other hand, when we are looking at active zone or the active region, we can call this as the amplifier circuit. Amplification, how BJT is used as an amplifier, we will discuss in module 4. It's not there in module 3. Okay, so that's why we are not going to detail about the active amplification or how it works, what are the circuits involved with it, but it will be discussed in module 4, next module. All right, so now I guess all the regions are clear how we are making this saturation active. So active means you can observe that it is almost going in par with the input supply. So IC, you can see IC is reaching its maximum and it's almost keeping constant throughout, even if you increase the VCB. So with VCB it is increasing. Every time I is more, you can see the IC is also increasing. Okay, so that's why it is active region. So same way in case of CE configuration, which we actually had done in lab, which we don't need to do right now because we already have experienced this in lab. So we can get a similar set of graphs and we can get the R in and R out. Remember one thing very important, that is input voltage. Whenever we are having an input voltage of 0.7, only after we are reaching the 0.7 we will have a corresponding output. So you can see this is where the 0.7 comes in. I told you in class as well, in lab class, that how we can get it. So again, after 0.7 almost, you can see there is a huge rise in the current that we are observing. Okay, and also I told you in lab as well that how we can expect that this VCE, with increasing VCE, the magnitude of IB is actually reduced. And that is again due to the early effect that we are looking at, because when we are increasing VCE, it means in a way we are reverse biasing the process, and as we are increasing the reverse biasing process, the depletion layer is extending it further, hence the effective width of the base will be reduced, hence the current will also be reduced. So in case of common emitter circuit as well, we can observe that this kind of a similar kind of pattern is experienced. Similarly, if I go on extending it for the output characteristics, this is also similar, because as we have already discussed in our lab, so the output characteristics, you can observe that it will be looking something like this. which we had experienced in lab already, so we don't need to discuss much on this. After this, after you can see after a certain period, you can see the last one, IC varies with VCE up to the knee voltage. Okay, so ICs varies up to the knee voltage. So here this is the knee voltage if I consider VP. Okay, so up to this point you can observe that with VCE, increasing VCE, we have a rising IC. But after the knee voltage is received, it actually is almost getting saturated for that particular value of IB. Okay, so this is again, this is, you can see this is constant. So this is basically the saturation current that we have received for each and every IB when the VV is constant. So you can see here it's mentioned this is the saturation region. So if you want a CE amplifier to be working, although it's not, usually CE amplifier works for the amplification purpose, but if I want to use it for the switch, okay, then we have to use it this saturation region or the cutoff region in order to make this as a switch, and only this active region will be used for the amplification purpose. So basically, if I have a transistor, I will decide on how the input voltages are to be triggered, okay, based on which we will control that the same device can operate in different applications. Alright, so that is how the process is. You can see the last point here, when VCE is further increased, over here somewhere, this particular point. So after that, what is happening? Depletion region increases, okay, same way leading to increase in the IC, because the base will be very small, and the transistor moves into a breakdown region, and hence this particular breakdown region is achieved. It's the same graph that we were obtaining over there as well, only the reverse part. Even you can observe that the one that we had gone in lab, we are not experiencing this part. Okay, we are not experiencing this one. So we are only getting up to the active region of this nature. Alright, so this is how the CE configuration is holding up. Alright, now let's discuss another thing that as I already told you. Just give me 1 minute. Yeah. So the one thing is that 90 to 95% of the transistor application are of CE type. So most of your numericals, most of your discussion, most of our discussions are revolving around CE. Because the reason is that it has a very high current gain. So the beta value, you can see IC is equal to beta IB plus ICEO, where ICEO is the leakage current. Okay, and this necessarily means that if beta is very high, that is what the fundamental idea about CE configuration is, then you can expect a very high IC, and IC is nothing but an output. So the output gain or the current gain is very high. Okay, so that is one of the advantage. Second is, as it has advantage of IC, naturally it will have a high voltage and a power gain as well. So naturally those things will be, because if one current is high, naturally the other process will also be equivalently high. And another thing is moderate output to input impedance ratio. What that means that easy to couple with other transistors as moderate ratio is observed for CE configuration. So you can couple multiple transistors together in order to form one particular segment. Alright, now let us discuss something which I need to come out of this presentation. Let me just do that, because those explanations will not be here. Okay. So let me just go back to my journal, right, and please make a note of it as well. All right, so this is after we have done the discussion on the several configurational challenges that we exist. Now let us try to investigate a little bit on the equations that we have devised so far. So the first thing that we come across, that this is for the common base. Okay, so I'll write it down for the common base configuration. Okay, for the common base configuration. So if we look closely at the common base expression that we have, is something like IC. Please make a note of this. This is not in the presentation. So IC is equal to IE or alpha IE plus ICBO. Okay, and this is coming from the straight from the idea that for a common base region, the base is grounded. Okay, and we have, if you go back to the diagram once again. So let me just go back to the diagram. This is my diagram. Yeah, this is my diagram. All right, and we look into the part over here. So this is my IB, the common configuration that we have. All right, so based on this we are trying to analyze the circuit a little bit. So now we can write that this is equal to IC equal to alpha IB IE plus ICBO. Why? Because we know that the IB, because we know that IB was equal to beta or IC by IB, sorry. So beta is equal to IC by IB. So this is IC by IE. That's what we have discussed. See, so this is IE, okay, and the beta value already we have established that in fact for some time. So beta was given by IC by sorry, alpha was given by IC by IE. So that's again we are writing over here. All right, so this is alpha. So I've written alpha, so that's why I'm writing. Now alpha E is fine. This part is what you can see, this is called as the leakage current. It usually stands for collector to base with emitter junction open. Okay, so that means in a way IE is equal to 0. Okay, there is still some current, there is still some current. All right, so that is the basic idea behind this. This is basically the leakage current that we were talking about. So if I need to rewrite this equation a little bit, I'm trying to incorporate a few parameters over here. So this is ICBO, and again IE is equal to IC plus IB. This already we had established long time back. Hopefully all of you remember this. So I substitute over here. All right, so IC is equal to IC plus IE is equal to IC plus let's put it this way, IC is equal to, yeah, so IC equals to alpha IE. So where is IE? Achha, then we can do it this way. So IE is equal to IC plus IB. So this is IC. Then maybe we can write IC plus IB plus ICPO. Okay, so we are substituting this equation over here. Okay, and why? Because we have an equation alpha IE. So instead of IE, we are writing IC plus IB. Now this is equal to alpha IC plus alpha IB plus ICB. Okay. Now if I take IC common, it becomes 1 minus alpha equal to alpha IB plus ICBO. Right. So we can also write IC is equal to alpha 1 minus alpha into IB plus ICBO by 1 minus alpha. So ideally this particular equation is ideally the exact equation that we need to follow in order to get the collector current for a CB configuration. Remember, this is we are doing for the CB configuration. The important part is that we are including this leakage current in the equation. Understood? Ideally, if you are neglecting this ICBO, it might create a problem in the overall rating of the transistor itself. So that's why this is to be included in your equation. So that's why we are looking at this particular parameter. Okay. Any doubt with this? Why we are doing it? This is for the common base. We are just investigating the common base a little bit. We have already established what is leakage current, why the leakage current is coming, and the conditions for leakage current. Now, if I include that leakage current in the equation that we already have established, we are getting the final expression as this. All right, just keep a note of this. Hopefully, all of you are all on the same page, right? This is fine now, okay? Is it fine, everyone?
Yes, sir.
Are you guys at all listening properly? What I mentioned? We are trying to include the leakage current in the equation. That's why we are modifying the existing equation by adding up this leakage current. because leakage current is a phenomena that will definitely happen in a transistor, whatever be the condition. So you have to include some way, although it is very small, but it has to be included somewhere. So that is what I'm trying to do over here. Instead of writing IC, which is a combination of IB and IE, we are now getting another expression for CB where it's only dependent on beta, alpha, because alpha is the current gain factor for a CB configuration. So naturally we can expect a similar kind of expression in terms of common emitter as well. So let's write that down. So for the common emitter one, okay, we will have the derivation is there in the course page. You can look into it later, and it will come something like IC is equal to alpha by 1 minus alpha. I want you to note it down, okay? The derivation is there in the page. 1 minus alpha into ICPO. Okay, so this whole term, okay, this whole term that you are looking at the right hand side, this is for CE configuration, remember. So what we have to do, we have to somehow convert this to beta. Okay, so this term eventually is called as ICEO. Just like we had it ICBO, we are replacing it with ICEO, which means collector to emitter current with base open. Collector to emitter current, I'll write it down. It means collector to emitter current with base open. Okay, so this is replaced by ICO. So what I can write, IC is equal to alpha by 1 minus alpha into IB plus ICEO. All right, and now in all these cases we have to replace this alpha by beta, because remember in CE configuration, if I go back, this beta was actually relevant to common emitter. So when we are looking at explaining the common emitter, we need to replace it by beta. So we come here, we replace this alpha by beta. So this will be IC equals to beta IB plus ICEO. Why? Because we had already proved that beta is equal to alpha by 1 minus alpha. This was already proven over here as well. It was already there here. Beta equals to alpha by 1 minus alpha. So the same thing I have applied over here. So this is another expression in which for common emitter, if I include the leakage current, then what should be the final expression? So please make a note of these two equations, this first equation here and the equation over here, because one is for common base and the other one is for common emitter. These equations are important, as I said, that suppose we have for a given supply, okay, we have for a given supply you have sufficient amount of information given to you. So in that way you can find out what are the collector or the base current associated with it. All right, so that is why these equations are important. So for example, I'll just take one small example before we end up this part. So please make a note of it. Suppose I have the collector leakage current. Suppose write down the question. Okay, the collector leakage current of a transistor is 300 microamps in CE configuration. Okay, so in CE configuration, the collector leakage current is given by 300 microamps. If now, the question is, if now the transistor is connected in CB configuration, okay, what will be the leakage current? See for yourself how we are comparing. Okay, what is the leakage current? So the same transistor is there, but it was used in a CE configuration. Now we are using it for the CB configuration. So how will the leakage current change? So you can observe that very simply we can write from the expression itself that ICEO is given as 300 microamps. Remember, I told you right now itself that this part is called as ICEO. This is only when it is in a common emitter circuit. Please understand and underline that part. If it is different configuration, the equations will change. But for it is a common emitter circuit, this is the final expression, and the portion that I dotted over here is called as ICEO, or the collector to emitter current with base open. So this ICEO is given as 300 microamps. All right, and as we know that ICEO can also be expressed as ICBO divided by 1 minus alpha. All right, so ICO equals to ICBO 1 minus alpha. This is also been established over here, ICBO by 1 minus alpha. Same thing I can write. So we can definitely, so we need a value of alpha. But in the configuration over here, okay, in this configuration over here, here one thing I missed is given here, given beta as 120. Otherwise we cannot solve it actually. So beta is equal to 120. So if I know beta equals to 120, so this is equal to, we can substitute alpha equals to beta by 1 plus beta. So this is 120 divided by 121, which is 0.992. So substituting this alpha value over here, we can say ICBO by 1 minus 0.992. So eventually, if we calculate, ICBO is coming as 2.4 microamps for the same configuration. So if you observe that in case of our common in case of our ICBO is for the common base, right? Common base current. So you can observe that with respect to can anyone quickly do this calculation and tell me if it is correct? I'm just having a doubt over here. 300 microamps, okay, multiplied by 1 minus 0.992. Can anyone quickly do it and tell me what will be the answer if it is correct? Is it in?
Yes, sir, it is coming out to be 2.4 microamps.
2.4 microamps, right? Okay, so it is fine. So it is around 2.4 microamps that we are observing over here. And in case of CE configuration, you can see the leakage current, it was there around 300 microamps. Okay, so that's how the process is that we are observing. Now, so you can observe that this is if you are including this microamps, this much of an amount of microamps current in your equation, like you normally when the calculations are done for transistors, we usually keep this as one of the specifications. So that's why this is important. Okay, so for most of the generic cases, you have to use this equation in general, given that you have all the data. Suppose in the question it's mentioned about ICBO, you have mentioned about ICEO, then only you can use it for your equation. Otherwise, you cannot assume it. Okay, you can't do it. In that case, you can keep it like IC plus IB equal to IE. The generic equation, you can use it. So this is about one part. The other parameter that is also very important accordingly, and that is called as a power rating of transistor. Okay. So this is basically the amount of power or the maximum power that the transmitter can handle without getting destroyed. That's the power rating. So it is ideally the maximum power that the transistor can handle before getting destroyed. All right, so this is a power rating. Simply what we can do, simple equation, PD is equal to collector current VC and the input voltage VCB. So this is about the equation for power rating. So it's collector current to that of the collector to base voltage. And in that way, if you observe that in the collector base, this collector VCB, this can also be neutralized in that way that if suppose VCB, if we look at VCB collected to base, that is equal to VBE plus VCB. So this is the total like how this VCB is generated. Collector to base terminal, this is base to emitter plus collector to base. This is what we can observe. And at times, if I ignore this VVE, which is very small, this can be very small, then ideally we can also say at times that if VVE is ignored, then only we can say that VCE, I think I made a mistake over here. This should be VC, both sides I have written VCE. This should be VCE. It should be VCE over here. All right, so VCE is equal to VCE is the collected to emitter voltage. So collected to emitter voltage is nothing but addition of base to emitter plus collected to base. So this total voltage is equal to collected to emitter. So that is what. So if this is VBE is very small, usually VBE is very small because it's the base to emitter voltage. It is very small compared to VBC. So what we usually have is that VCE is nearly equal to VCB. Okay, so in that way, what we can do is that this equation here, we can at times, if VBE is small, we can actually replace this by VCE as well. Okay, so that is how the power rating works. Okay, so like given a particular specification, you can find out what is the power rating. And power rating, why it is important, because based on this only you can use the transistor for operations where the power dissipation might be very high. For some cases, just for example, just take an example like this. For example, suppose I have a power rating as 300 milliwatt. Okay, suppose the power rating is 300 milliwatt of a transistor. This is the maximum power that it can withstand. So IC is given as 30 milliamps. So question is, what is the maximum VCE? Okay, what is the maximum VCE? Maximum VCE means collected to emitter terminal. If I put a voltmeter, what will be the maximum reading? So you can simply observe that if I consider PD is equal to IC multiplied by VCE. This is equivalently. Whenever it is asking to find out VCE, it means the VVE is ignored. It's less. So we can say IC simply VCE is nothing but PD, which is 300 milliwatt divided by IC, which is 330 milliamps. Now very carefully you observe one thing. So this 10 volt, if it is, that means, so for the conclusion is, so for IC equals to 30 milliamps, okay, the maximum VCE is allowed, which is 10 volt. So if you go beyond 10 volt, if the voltage exceeds beyond 10 volt, the BJT or the transistor might get damaged. Understand? So if you are using a transistor and you are using it in a circuit, you are restricted with the collector to emitter terminal voltage to be kept within 10 volts. What I mean is, suppose you have a transistor like this. Suppose this is a basic circuit. You have a voltage like this, okay, and you have a supply voltage of this nature maybe. Okay, now this is my collector, base, and emitter. Right now, collector to emitter voltage means if I connect a voltmeter like this, whatever the reading we are getting. Now this value is 10 volt. This drop should be not more than 10 volt. Now based on that, what you can do, you can change this voltage supply so that this transistor can operate without getting burned. All right, understood. That is basically what the power rating is of a transistor. And if that you require that in an application where you have to have more power, when the power dissipation can be more, then instead of normal transistor, we use something called as power transistor. Power transistor is something which is commonly used in analog circuits. This is not there in your syllabus, but in power transistor, what happens? The base region is actually pretty big. Okay, and the collector is even bigger. Okay, so that's why the power transistor happens. It has a heat sink also added to it, so that the heat dissipated can be completely taken care of. All right, so that is how the power is working. Like these are the parameters for it. Right, so this is about the discussion on the specification and the parameters related to CECB configuration and the process involved with it. But one thing we have not discussed, which where we end our discussion today, and that is interesting, and that is called as transistor as a switch. Okay, so this is what we had already discussed as per the diagram. If you observe that I had already told you that when and why the switching is happening. So, for example, sorry. So if I go back, so this is one of the case when cutoff is happening, okay, and one and the other one was when we discussed over here that active region was used for amplification, and I told you that saturation region is also for switch. So that is now the point is how we can do that. So transistor as a switch or an amplifier, as I said, the amplifier we are not going to discuss over here. We will discuss it in the fourth module. So the amplifier part, we will specifically, this is for the active region. So we are neglecting for the time being with our discussion. What we are going to discuss is transistor as a switch in two cases. One is when it is at saturation region. Hopefully by now you know what is saturation region, and by this is when it is in cutoff region. This is, see, this region will only, it will be existing in any transistor. The way you are operating the transistor to reach this cutoff or saturation is where the engineering lies. Understood? So all the transistor, if you want to keep it in the saturation region, you have to accordingly supply the voltage control, the VCE, so that we can keep it within the saturation region, or otherwise. Understood? So there is no hard and fast rule that a transistor will only be acting as an active amplifier and you cannot use it as a switch. You can use it, but in that case you have to modify the circuit accordingly. Now the thing is, if I use the cutoff region, this cutoff region, the switch is what we usually look into, is called as the open switch. Okay, whereas in saturation we called it the closed switch condition. Now let's see what exactly it is. One is the opposite of the other. So any one, if I explain, the other one will be the opposite to it. Now what happens, you can observe that, let me just draw the circuit for the open switch. Okay, we'll take the cutoff only. So let's draw the circuit over here. Okay, so suppose I have a base. This is a common emitter circuit once again, and we have a common terminal over here. We have a supply VBB like this. Okay, and we have a RC maybe like this, RC, and we have a supply voltage once again, and we have like this. And suppose these are all variable voltage, like we are arranging it. So this is my RB, this is my RC collector resistance, okay, and this is my IC, this is my IB, okay, this is my IB. There's the base current, collector current, and IE current also is present. All right, this is an NPN transistor. I'm not repeating the nomenclature and all, hoping that you all know it. Now across this, as I said, if I consider these 2 points across these two terminal, okay, and I measure the voltage, this will be nothing but the VCE voltage, collector to emitter voltage. This is my collector, this is base, and this is emitter. Right? This is, all of you agree, right? Now in this case, when we are looking at cutoff region, what happens that we are keeping both the junction, please make a note of this, please, both the junctions are reverse biased. All right, so that means the collector to base and emitter to collector, both the junction are reverse bias. In that case, what will happen, as it will be having a reverse bias, that and ideally reverse bias means that a very small current, minority current will go on, which is basically the leakage current we have told you. So in that case, the condition is that IB will be 0 and my IC will also be 0, because ideally there is no input. Basically we are giving no input. In fact, if it is reverse bias at this end as well as reverse bias at this end, basically we are allowing the transistor not to operate. And if it is not operating, that means the base and the collector current will be 0 ideally. So if these two are 0, okay, if these two are 0, so if you observe that if I apply the Kirchhoff's voltage law in this second loop, suppose this is my loop 1 and this is my loop 2. Right? So in that case, what we are looking at, VCC is equal to ICRC plus VCE. So I'm mentioning this as VCE and this is as VBB. This is VCC. Yeah, sorry, this is VCC. Okay. So this name also, I don't think there will be much problem because we have done that in lab as well. So this is the power supply. We are mentioning it as VCC and VBB. The drop across collector to emitter is considered as VCE. Now I apply the KVL on this second loop. Okay. So VCC is equal to ICRC. IC is passing through this resistor, so ICRC plus VCE. Now, as per our assumption, since both the sides are reverse bias, what is happening? IC is equal to 0. So 0 into RC plus VCE. So this is 0. Okay, so that means VCC is equal to VCE. So now observe the significance of it. In this condition, you can observe, okay, the output, okay, the VCC is reflected as the output because we are taking the voltmeter over here, we are making the measurement over here. So the output is VCE, okay, so the VCE is high, but at that point IC is equal to 0 because we have already assumed that. Now IC is equal to 0 because of the reverse bias, okay, because how we are operating it. IC is 0, but we are getting a very high input. So what does that mean? The input is 0. That means the input is 0. Input is 0, but we are getting an output, or the output we are generating is like something of this nature. The transistor is not operating. It is like this. Like we have a resistance. Okay. The transistor is acting like something like this. Suppose this is as an open switch. You can say open switch, okay, and this is where we are tapping out VCE. So the whole of VCC is flowing towards this direction. As this is open circuit, nothing is coming out of the terminal, like there is no drop across transistor, everything is coming in over here, VCE. So it's basically an open switch. The transistor is acting as an open switch, as if it is only allowing this whole supply to be available at the output. So if you observe carefully, if I draw a small little graph over here, okay, so if suppose this is my input and this is my output, okay, so if input is low, we are getting a value high point of output because output is determined by VCC. So this value will go on like this, okay, up to a certain point. In fact, up to this point, suppose this is 0.7 volt. So this value is where the cutoff is worked on. So if you are observing, if you are working the transistor in a cutoff region, then the transistor is behaving as an open switch, and thus the supply voltage is received over here. Remember, at this point the input is 0, so that's why the input is 0, but the output we are getting. So that's why the graph is looking like this. And after this, what will happen? After this, suppose we are applying some amount of voltage. Over here. Suppose we are applying some voltage over here is the input. Okay. Now, as we are giving little bit of input over here, naturally, what will happen? This IC won't be 0. There will be some amount of drop, and as there will be some amount of drop, naturally, my voltage curve will come down. Will look like this. It will come like this up to a certain extent. Okay, up to a certain point. This point is basically the saturation voltage, V saturation, and after that it will go like this. Okay, so this portion, the one that I'm written over here, is called as the saturation. This is active. All right, so as if this is the voltage versus voltage graph. So in case of the saturation, the second part which I told you over here, what is happening that this is acting as a closed switch. That's because when you are applying the input voltage, and even it's a very big high value of input voltage you are applying on it, okay, the more the voltage you are applying on it, the voltage will tend to come down, and after a certain period it will reach to the saturation point. How the conditions should be? So the saturation part, let's do that. So the condition that we have to impose is that IB should be sufficiently greater or greater than equal to, if I'm right, is equal to IC saturation divided by beta. So this is the condition. By properly changing the input voltage, the resistance associated with it, we actually can maneuver such that IB satisfies this particular condition. All right, if this condition exists, then naturally what will happen, the VCE will be very small, and hence it will be reducing. So you can see that this is coming down over here. Sharply it will come down, and it will stay constant throughout. Even if you increase the input voltage, even if you increase the input voltage, there is hardly any change in the output. Output is remaining as it is. In cutoff, what was happening? Low voltage, high output, but here saturation, what is happening, with increase, no output. Okay, so that is the difference of it. In that saturation mode, they act as a closed switch. So the circuit would look something like this, maybe transistor. This is VCC. Now the transistor is acting like a closed switch. This is my transistor actually, and this is the output we are gathering. And this VCE will be very small. Collector to emitter voltage, why it will be very small? Because the IC will be very high, because you are feeding in more power, more current. So what will happen, this equation, if you observe, this will be increasing more and this will be reducing less, like this, it will go down. And as the collector to emitter voltage will be dropping, we will be not getting naturally, you will be not getting much as an output. So you are observing that even if you increase the input, you are not getting any output. So even if you increase the input, output is less. Alright, so that is where it is acting as a switch, a transistor as a switch in general, either open switch or a closed switch, the way you are looking at it, based on the operating condition at which the transistor is being operated, either in saturation or in cutoff. In active region, it will be specifically for the amplifier stage, which we are going to discuss in fourth module when the amplifier circuit will come. All right, so I think this is all that I need to tell you for today. A little more, we are stretched a little bit more today. So hopefully you will go through the material when I upload by today. Most probably, I was waiting to finish off this segment, and then only I was thinking of uploading. So I'll upload all these materials by today itself, so that you can look into it. And given the fact that we are going to start off with the MOSFET in the next class, please make sure that you at least go through it a little bit, because most probably next week sometime I will be planning for the quiz also, where the syllabus will be up to the Cat 1 portion, as well as the portion of transistor will definitely be there. Alright, so that's why I'll let you know about the dates. So, but you please be prepared with this part also. So I'll be uploading the materials, you look into it. All right, anyone having any doubt regarding anything?